Take a slow breath in, and as you gently breathe out, imagine the solid ground beneath you. It feels still, dependable, and calm. Tonight, we're going to explore a fascinating truth about our planet. Even when everything feels quiet, Earth is always moving, always reshaping itself in slow and patient ways that span millions of years. Welcome to this calming journey through earthquake facts and plate tectonics. Designed to be reassuring, educational, and softly narrated so you can relax, unwind, and drift toward sleep. Whether you are listening late at night, during a quiet afternoon, or while traveling across time zones, this video is meant to feel like a gentle companion. There's no urgency here. Only curiosity, calm science, and the steady rhythm of Earth itself. If you enjoy relaxing, educational content like this, you're warmly invited to like the video and subscribe to the channel. And if it feels right, you can leave a comment sharing your country, your city, and the time you're watching or listening. It's always peaceful to see how people from around the world gather together under the same ideas, even as tectonic plates quietly move beneath us all. Now, let's begin softly. Earthquakes can sound intimidating at first. The word itself often brings dramatic images to mind. But at their core, earthquakes are simply the result of natural processes that have been shaping our planet for billions of years. They are not signs of chaos, but evidence of balance, release, and renewal in Earth's vast geological system. Our planet is layered, like a carefully constructed story. At the very center lies the core, hot and dense, generating the magnetic field that protects us from solar radiation. Surrounding it is the mantle, thick and slowly flowing, moving at a pace far slower than any river you've seen, yet powerful beyond imagination. On top of it all rests the crust, the thin outer shell where oceans, mountains, cities, and civilizations exist. This crust is broken into pieces known as tectonic plates. These tectonic plates are enormous. Some carry entire continents. Others support vast stretches of ocean floor. They move slowly, often no faster than the growth of a fingernail each year. And yet, over time, their movement builds mountains, opens oceans, shapes coastlines, and, occasionally, releases energy in the form of earthquakes. One calming fact to remember is this: earthquakes are not random. They follow patterns governed by physics, pressure, and time. Most occur along plate boundaries, where plates meet, slide past one another, pull apart, or gently collide. These boundaries form some of the most dramatic landscapes on Earth, including deep ocean trenches, volcanic arcs, and some of the world's most famous travel destinations. Think of the Pacific Ring of Fire, for example. It's a vast horseshoe-shaped zone surrounding the Pacific Ocean, home to many earthquakes and volcanoes. Despite its dramatic name, this region includes places of extraordinary beauty and cultural richness. From Japan and New Zealand to Chile and California, millions of people live full, vibrant lives there, supported by modern engineering, technology, and education that work alongside Earth's natural rhythms. Earthquakes happen when stress builds up along a fault line. A fault is simply a fracture in the Earth's crust where blocks of rock move relative to each other. Over time, tectonic forces push and pull these blocks, but friction holds them in place. Eventually, when the stress becomes too great, the rocks slip, releasing energy that travels through the earth as seismic waves. These waves are what we feel as shaking. Some move quickly, others roll gently, and many pass unnoticed, except by sensitive instruments. In fact, the vast majority of earthquakes are so small that humans never feel them at all. Every day, thousands of tiny earthquakes quietly ripple through the planet, adjusting pressure, relieving stress, and maintaining balance deep below the surface. Scientists measure earthquakes using seismographs, instruments that record ground motion with incredible precision. From these measurements, researchers determine an earthquake's magnitude, depth, and location. This data supports global education, safer construction, disaster preparedness, and even insurance and economic planning in earthquake-prone regions. It's comforting to know that this science is shared internationally. Countries collaborate, exchanging data and research to better understand tectonic behavior. From universities and research centers to space agencies and geological surveys, earthquake science connects technology, education, and global cooperation. Another reassuring truth is that earthquakes do not create new danger out of nowhere. They release energy that has been building gradually over long periods of time. In many ways, earthquakes are Earth's way of maintaining equilibrium. Like a deep stretch after holding tension for too long. As you listen, you might imagine tectonic plates drifting slowly, far beneath oceans and cities, their movements measured in millimeters and centuries. Above them, rivers flow, cultures develop, economies grow, travelers explore new places, and life continues with remarkable resilience. Throughout this series, we'll explore earthquake facts in a calm, sleep-friendly way. We'll learn about different types of faults, why some earthquakes are deep while others are shallow, how seismic waves travel through rock, and how ancient civilizations understood earthquakes long before modern science existed. We'll also gently touch on how modern architecture, engineering, and urban planning work with tectonic realities, allowing cities to thrive even in active regions. From luxury hotels designed to sway safely, to historic temples that have endured centuries of seismic motion, human ingenuity often mirrors Earth's patience and adaptability. For now, let your mind rest on this simple idea. Earth is not fragile. It is dynamic, resilient, and deeply balanced. Mineral resources and the very continents we call home. As we continue, the facts will unfold slowly, like layers of rock revealed over time. There's no need to remember everything. Just listen, breathe, and allow the quiet science of plate tectonics to guide you gently toward rest. As you settle more deeply into stillness, let's gently drift back in time to an era when Earth was thought to be solid and unchanging. For most of human history, people believed continents were fixed in place, anchored forever where they stood. Mountains were seen as permanent, oceans as eternal, and the ground beneath our feet as something that did not wander. Yet, the planet, as we now know, tells a much softer and more surprising story. The idea that Earth's surface could move was once considered almost unthinkable. But in the early 20th century, a quiet and persistent scientist named Alfred Wigtiner began noticing patterns that seemed too perfect to ignore. As you listen, imagine him studying maps by lamplight, tracing coastlines with his eyes, letting curiosity guide him. Wigtiner observed that the eastern edge of South America and the western edge of Africa fit together like pieces of a gentle puzzle. Not perfectly, but closely enough to raise questions. He noticed similar fossil species on continents now separated by vast oceans. Ancient plants and animals appeared on land masses thousands of kilometers apart, as if they had once shared the same home. In 1912, Wigtiner proposed the theory of continental drift. He suggested that all continents were once joined together in a single supercontinent, which he called Pangaea. Over millions of years, he believed this massive landform slowly broke apart, with continents drifting to their present locations. At the time, the idea was deeply controversial. Many scientists resisted it, not because the evidence was weak, but because there was no known mechanism to explain how continents could move. Rocks seemed too rigid. Earth seemed too solid. Wigtiner's theory lacked the underlying physics needed to convince the scientific world. Still, the idea lingered quietly like a seed resting in soil. Decades later, advances in technology began to reveal what human senses alone could not. During and after World War II, scientists used sonar to map the ocean floor in greater detail than ever before. What they found was astonishing. Beneath the calm surfaces of the world's oceans lay vast mountain ranges, deep trenches, and long cracks stretching for thousands of kilometers. These mid-ocean ridges became one of the most important clues in Earth's science. Along them, molten rock rises from the mantle, cools, and forms new oceanic crust. This process, known as seafloor spreading, showed that Earth's surface was not only moving, but constantly renewing itself. As new crust forms at ridges, older crust must move away. Eventually, it sinks back into the mantle at deep ocean trenches in a process called subduction. This slow cycle of creation and recycling revealed the engine Wigtiner had been missing. By the 1960s, the theory of plate tectonics emerged, uniting continental drift, seafloor spreading, and earthquake science into one elegant explanation. The Earth's crust was no longer seen as a single, unbroken shell, but as a mosaic of tectonic plates floating atop the semi-fluid mantle. This realization transformed geology, geography, and education worldwide. It explained not only earthquakes, but also volcanoes, mountain ranges, and the distribution of natural resources. It helped clarify why some regions are rich in minerals, why certain landscapes attract tourism, and why fertile soils often appear near tectonic boundaries. Think of the Himalayas rising slowly as the Indian plate presses into the Eurasian plate. This gentle but persistent collision continues today, lifting the mountains millimeter by millimeter. It's a reminder that even the tallest peaks are part of an ongoing process shaped by patience rather than force. Or consider Iceland, a popular travel destination known for its dramatic scenery, geothermal spas, and volcanic landscapes. It sits directly atop the mid-Atlantic ridge, where two tectonic plates pull apart. The island exists because of this slow separation, where magma rises and creates new land. Tourism culture, and nature, they are all connected to tectonic movement. Earthquakes fit naturally into this story. They often occur where plates interact, storing and releasing energy as they move. Some earthquakes happen at convergent boundaries, where plates collide. Others occur at divergent boundaries, where plates separate. Still, others happen along transform faults, where plates slide past each other horizontally. One famous example is the San Andreas Fault in California, a transform boundary where the Pacific Plate and the North American Plate move side by side. The motion is slow and steady, but stress builds over time. When it releases, the ground shifts briefly, then returns to quiet. It's important to remember that these movements are normal. They are part of Earth's long-term balance. Without plate tectonics, our planet would look very different. There would be fewer mountains, less recycling of carbon, and possibly a climate far less suitable for life. Plate tectonics even plays a role in Earth's ability to support oceans and atmosphere over billions of years. By cycling materials between the surface and the interior, it helps regulate temperature and chemical balance. In this way, earthquakes and tectonic movement are woven into the deeper story of habitability. As science progressed, so did the tools used to study earthquakes. Modern seismology uses networks of sensors placed around the globe, sharing data in real time. This international cooperation supports early warning systems, safer infrastructure, and better urban planning. Cities in earthquake-prone regions often lead innovation in architecture and engineering. Buildings are designed to sway gently rather than resist motion. Bridges incorporate flexible joints. Luxury hotels, cultural landmarks, and transportation systems all benefit from this careful design, blending safety with comfort and beauty. Education plays a central role as well. Understanding plate tectonics empowers communities, reduces fear, and replaces uncertainty with knowledge. When people understand why earthquakes happen, they often feel more at ease, better prepared, and more connected to the planet beneath them. As you rest, imagine the continents drifting slowly, almost imperceptibly, guided by forces deep within the earth. This movement is not rushed. It follows rhythms measured in millions of years. It is steady, quiet, and purposeful. As your breathing slows and your thoughts drift, let's move softly into one of the most important ideas in earthquake science: the boundaries where tectonic plates meet. These boundaries are not sharp lines you could trace on the ground. Instead, they are wide zones of interaction, stretching 4 kilometers, where Earth's slow motion becomes quietly visible through mountains, valleys, volcanoes, and earthquakes. There are 3 main types of plate boundaries, and each one speaks a slightly different geological language. Understanding them helps transform earthquakes from sudden mysteries into part of a calm, predictable system. The first type is called a divergent boundary. This is where tectonic plates slowly move away from each other. Imagine 2 massive slabs of earth gently drifting apart, creating space between them. From deep below, molten rock rises to fill that gap. When it cools, it becomes new crust. Most divergent boundaries lie beneath the oceans. The Mid-Atlantic Ridge is one of the most famous examples. It runs like a quiet seam down the center of the Atlantic Ocean, separating the Americas from Europe and Africa. Along this ridge, new ocean floor is constantly forming, though the process is so slow that it feels timeless. At divergent boundaries, earthquakes tend to be smaller and less intense. The motion is gradual, and the Earth releases energy frequently, preventing large stress buildup. These earthquakes are often shallow and brief, sometimes unnoticed, except by sensitive instruments. Divergent boundaries also shape unique landscapes. In Iceland, where divergent boundary rises above sea level, you can walk between two continents. The island's lava fields, geysers, and warm geothermal pools have become major attractions for tourism and wellness travel. Luxury spas, like the Blue Lagoon, owe their existence to tectonic forces quietly working beneath the surface. The second type of boundary is called a convergent boundary. This is where tectonic plates move toward each other. When they meet, something has to give. Often, one plate is forced beneath the other in a process called subduction. Subduction zones are some of the most powerful earthquake-producing regions on Earth. As one plate sinks into the mantle, it doesn't slide smoothly. Instead, it sticks, bends, and stores energy. When that energy is released, the ground shakes. Many of the world's largest earthquakes occur along subduction zones. The Pacific Ring of Fire, a horseshoe-shaped region surrounding the Pacific Ocean, is filled with these boundaries. Countries like Japan, Chile, Indonesia, and New Zealand experience frequent earthquakes because they sit along these active margins. Yet, convergent boundaries are not only zones of risk. They are also places of extraordinary natural beauty and cultural depth. Japan's mountainous landscapes, hot springs, and fertile soils are shaped by subduction. These geological features support agriculture, tourism, and centuries-old traditions connected to nature. In some convergent boundaries, two continental plates collide instead of one subducting beneath the other. Because continental crust is buoyant, neither plate easily sinks. Instead, the crust crumples and thickens, forming massive mountain ranges. The Himalayas are the most dramatic example. The Indian plate continues to push into the Eurasian plate, raising the mountains higher over time. Earthquakes in this region reflect the ongoing compression, but the motion is steady and slow, measured in centimeters per year. Mountain-building collisions influence climate, ecosystems, and even global weather patterns. High elevations affect wind flow and rainfall, shaping rivers and valleys far beyond the mountains themselves. These processes influence human settlement, trade routes, and economic development across entire regions. The third major type of boundary is called a transform boundary. Here, tectonic plates slide past one another horizontally. They neither create new crust nor destroy old crust. Instead, they grind along their edges, sometimes smoothly, sometimes with resistance. Transform boundaries are responsible for some of the most well-known earthquakes. The San Andreas Fault in California is a classic example. The Pacific Plate moves northwest relative to the North American Plate. Most of the time, this motion is imperceptible. But when friction locks the plates together, stress builds. Eventually, that stress is released suddenly, producing an earthquake. Afterward, the plates continue their slow journey, as if nothing unusual had happened. Transform earthquakes can be strong, but they are usually shallow. This means the shaking can feel intense near the surface, even if the overall energy release is smaller than that of deep subduction earthquakes. Regions near transform boundaries often invest heavily in earthquake-resistant design. Cities like San Francisco and Los Angeles have become leaders in seismic engineering. Buildings are designed to flex gently, absorbing motion rather than resisting it. This blending of technology, education, and urban planning reflects how societies adapt to Earth's rhythms. What's comforting to remember is that earthquakes are not signs of instability or failure. They are signs of motion continuing as expected. The Earth is doing what it has always done. Scientists monitor plate boundaries using GPS stations that measure movement with millimeter precision. These tools allow researchers to watch continents drift in real time, offering insights that were unimaginable just a century ago. This data supports early warning systems that can detect the first waves of an earthquake and send alerts before stronger shaking arrives. Even a few seconds of warning can protect lives, slow trains, stop surgeries, and secure sensitive equipment. Around the world, education programs teach people how to respond calmly during earthquakes. Simple actions like moving away from windows or taking shelter under sturdy furniture reduce injury risk significantly. Knowledge replaces fear with confidence. In quieter moments, plate boundaries remind us that Earth is not static. It is alive with motion, yet governed by order. The same forces that cause earthquakes also create coastlines, islands, and fertile plains. Many of the world's most iconic travel destinations exist because of plate boundaries. The Andes, the Alps, the Japanese archipelago, and the islands of the Pacific all owe their beauty to tectonic processes. Culture, cuisine, architecture, and history in these regions are deeply shaped by geology. As you rest, imagine the plates beneath you moving like slow dancers, guided by gravity and heat, never colliding by accident, always following physical laws. Their movements are measured in patience, not urgency. As the night grows quieter and your thoughts slow, let's gently explore what actually happens during an earthquake. Not in a dramatic way, but calmly, step by step, as if we are watching the process unfold from a peaceful distance. Understanding this sequence often replaces anxiety with reassurance. Because earthquakes follow clear physical rules, not chaos. Deep within the Earth's crust, tectonic plates are always moving. Most of the time, their edges are locked together by friction. Even though the plates want to slide, that friction holds them in place. As motion continues, stress builds slowly, almost invisibly, like pressure accumulating in a tightly closed book. This stored energy can remain locked for years, decades, or even centuries. The rocks near a fault bend slightly under the pressure, behaving almost like a compressed spring. This bending is called elastic deformation, and it is a normal, expected part of tectonic motion. An earthquake begins when the stress becomes too great for the rocks to hold. At that moment, the fault slips. The stored energy is released suddenly, and the rocks snap back toward their original shape. This release happens very quickly, often in just a few seconds, even though the stress may have built up over a long time. The exact point where the fault begins to slip is called the focus or hypocenter. This point lies beneath the Earth's surface. Directly above it, on the ground, is a point called the epicenter. While the epicenter often gets the most attention, it's the focus that truly marks the beginning of the earthquake. From the focus, energy travels outward in the form of seismic waves. These waves move through rock, soil, and even the Earth's core, carrying the motion we feel at the surface. Scientists study these waves carefully because they reveal what the Earth is made of deep below. The first waves to arrive are called primary waves, or P waves. They move the fastest and travel through both solid and liquid material. P waves compress and expand the ground in the same direction they travel, like a gentle pulse. Most people don't feel them strongly, if at all. Come secondary waves, or S waves. These move more slowly and only travel through solid materials. S waves move the ground side to side, or up and down, perpendicular to their direction of travel. This is often the first motion people actually feel. After the body waves come surface waves, which travel along the Earth's surface. These waves tend to cause the most noticeable shaking and damage. They move more slowly, but with larger motions, gently rolling or swaying the ground like ocean waves. It's important to remember that shaking intensity varies widely. Distance from the epicenter, depth of the focus, local geology, and building design all influence how an earthquake feels. Two people just a few kilometers apart can experience very different levels of motion. Soft soils, like sand or clay, can amplify shaking. This is why earthquakes often feel stronger in river valleys or coastal plains. Bedrock, on the other hand, tends to transmit waves more steadily, reducing amplification. This relationship between geology and shaking has shaped urban planning and construction practices around the world. Cities invest heavily in seismic studies to understand how local ground conditions behave. This knowledge guides safer development, protecting homes, schools, and critical infrastructure. The duration of shaking is another important factor. Many earthquakes last only a few seconds. Even strong earthquakes often release their energy quickly. Longer shaking tends to occur in very large earthquakes or in areas with complex fault systems. After the main earthquake, smaller movements called aftershocks often follow. These are not separate events, but adjustments as the crust settles into its new position. Aftershocks are usually weaker, though they can still be felt and occasionally cause damage. Scientists cannot predict exactly when an earthquake will occur, but they understand where they are more likely. Fault maps, historical records, and plate boundary data allow researchers to identify higher-risk zones with impressive accuracy. This knowledge supports preparedness rather than fear. In earthquake-prone regions, emergency systems, building codes, and public education reduce risks significantly. Over time, communities learn to live comfortably with tectonic activity. Technology has further improved safety. Seismometers can detect P waves almost instantly. Because P waves travel faster than damaging waves, early warning systems can send alerts seconds before strong shaking begins. Those seconds matter. Trains can slow. Factory machines can shut down. Elevators can stop at safe floors. And people can move to safer positions. This blend of science and technology quietly protects millions of people every day. Earthquakes also play a role in shaping landscapes over geological time. They can raise land, alter river paths, and create new landforms. Over millions of years, these changes influence ecosystems, agriculture, and even global climate patterns. From a broader perspective, earthquakes are part of Earth's natural balance. Without tectonic movement, continents would erode flat, nutrients would not recycle efficiently, and the planet would lose much of its dynamic character. As you rest, imagine the Earth releasing tension the way a deep breath releases stress from your own body. The shaking passes, the ground settles, and balance returns. As your breathing slows and the quiet settles in, we can now turn to one of the most misunderstood aspects of earthquakes: how they are measured. Numbers like magnitude and intensity often sound alarming when mentioned in news headlines, but when explained gently, they become calm. Logical tools that help scientists understand Earth's movements more clearly. Let's begin with magnitude. Magnitude is a measure of the total energy released by an earthquake at its source. It does not describe damage, fear, or impact on people. It is simply a physical calculation, much like measuring the brightness of a star or the strength of a radio signal. Today, scientists most commonly use the moment magnitude scale, often written as MW. This scale replaced the older Richter scale for most scientific purposes because it works accurately for both small and very large earthquakes. The moment magnitude scale considers the area of the fault that slipped, the amount of slip, and the strength of the rocks involved. Each whole number increase on the magnitude scale represents about 32 times more released energy. This sounds dramatic, but remember, energy release does not automatically translate into destruction. Many high-magnitude earthquakes occur deep underground or far from populated areas and cause little disruption. A magnitude 2 earthquake, for example, happens thousands of times a day around the world. Most people never feel them. A magnitude 4 might be felt as a gentle shaking, similar to a heavy truck passing nearby. Even magnitude 5 earthquakes often cause minimal damage when buildings are well designed. Larger earthquakes, such as magnitude 7 or higher, are rare. They occur mostly along major plate boundaries, often in remote oceanic regions. When they do occur near populated areas, preparation and building standards play a far greater role in outcomes than the number itself. Now, let's gently introduce intensity. While magnitude measures energy at the source, intensity describes the effects of shaking at a specific location. Intensity varies from place to place during the same earthquake. One town may feel light shaking, while another experiences stronger motion. This scale uses Roman numerals from I to 12. Rather than instruments, it relies on observations, what people felt, how objects moved, and whether structures were affected. An intensity of I means the earthquake was not felt at all. An intensity of 3 might feel like a soft vibration, noticeable only to people at rest. By the time intensity reaches 5, people may feel strong, shaking, and unsecured objects might move. Higher intensities describe more significant effects, but again, these depend heavily on local conditions. Ground type, building materials, and distance from the epicenter all influence intensity. This is why two earthquakes of the same magnitude can have very different impacts. Modern seismology combines both magnitude and intensity to create detailed maps. These maps help emergency planners, insurers, engineers, and governments make informed decisions. They guide investments in safer buildings, infrastructure, and education. Seismometers are the instruments that record earthquake waves. They are incredibly sensitive, able to detect ground motions smaller than the width of a human hair. Networks of seismometers operate quietly all over the world, continuously listening to Earth's movements. When an earthquake occurs, data from many stations are combined. By comparing arrival times of P waves and S waves, scientists can pinpoint the earthquake's location and depth. This process happens quickly, often within minutes or even seconds. This rapid analysis supports global communication and early response. Airlines adjust routes, shipping companies assess ports, and international monitoring agencies track seismic activity across continents and oceans. It's worth noting that earthquakes are not increasing in number. With better instruments and communication, we simply detect and report more of them. The Earth's tectonic rhythm remains steady over long timescales. Education plays a key role in public calm. When people understand what earthquake measurements truly mean, fear gives way to awareness. Knowledge transforms uncertainty into confidence. Even the language used around earthquakes is evolving. Scientists now emphasize resilience, preparedness, and adaptability. Communities are seen not as victims of geology, but as partners with it. As you relax, imagine these measurements not as warnings, but as gentle signals. They are Earth's way of communicating its internal movements, translated into numbers that help humans coexist safely with a dynamic planet. As the night grows quieter, let's gently drift across the surface of our planet and explore where earthquakes tend to occur most often. This journey is not about danger or fear. Ancient patterns written into the geography of Earth itself. Earthquakes are not evenly distributed around the globe. Instead, they follow invisible lines where tectonic plates meet, slide, collide, or slowly pull apart. These regions are known as seismic zones, and they form a kind of living map of Earth's internal motion. One of the most well-known seismic regions is the Pacific Ring of Fire. This horseshoe-shaped zone curves around the edges of the Pacific Ocean, touching the western coasts of North and South America, continuing through Alaska, Japan, Southeast Asia, and down toward New Zealand. About 75% of the world's active volcanoes, and roughly 90% of its earthquakes occur within this vast region. The Ring of Fire exists because several major tectonic plates, in many places, dense oceanic plates slowly sink beneath lighter continental plates in a process called subduction. As these plates move, stress builds and releases in the form of earthquakes. Despite its dramatic name, life continues peacefully for millions of people within the Ring of Fire. Countries like Japan, Chile, and New Zealand have adapted through advanced engineering, education, and technology. Earthquake science has become part of daily life, supporting safer cities, resilient economies, and innovative architecture. Moving westward, we encounter the alpine Himalayan seismic belt. This zone stretches from southern Europe through the Middle East and into South Asia. It includes regions like Italy, Greece, Turkey, Iran, and the towering Himalayas. Here, massive continental plates are slowly colliding. The Indian plate continues its gentle push into the Eurasian plate, uplifting the Himalayas by a few millimeters each year. Earthquakes in this region are part of the same process that created the world's highest mountains. These regions are also deeply tied to human history and culture. Ancient civilizations developed along tectonically active landscapes, drawn by fertile soils, trade routes, and water sources shaped by geology. Even today, tourism thrives in these areas, blending natural beauty, history, and modern infrastructure. Another important seismic region lies along mid-ocean ridges. These underwater mountain chains run through the Atlantic, Indian, and Pacific Oceans. Here, tectonic plates slowly pull apart, allowing magma to rise and create new oceanic crust. Earthquakes along mid-ocean ridges are usually small and gentle. They happen frequently, but rarely affect human populations because they occur deep beneath the sea. These quiet earthquakes play a crucial role in shaping Earth's surface over millions of years. Transform boundaries form another category of seismic zones. Along these boundaries, plates slide past one another horizontally. The San Andreas Fault in California is a well-known example. Rather than creating mountains or volcanoes, transform faults create linear valleys, offset rivers, and subtle shifts in landscapes. Earthquakes along transform faults tend to be shallow, which means they can be felt more strongly at the surface. This is why urban planning and engineering are especially important in these areas. Modern technology, smart design, and education have significantly reduced risks. Intraplate earthquakes are less common, but equally fascinating. These occur far from plate boundaries, within the interior of tectonic plates. The New Madrid seismic zone in the central United States is one example. Scientists believe intraplate earthquakes happen due to ancient faults reactivating under modern stresses. These events remind us that Earth's history is layered with past movements influencing present behavior. Globally, seismic monitoring networks quietly observe all these regions. Data flows continuously between countries, supporting international cooperation and shared scientific understanding. Earthquake science has become a global language, connecting nations through education, technology, and preparedness. Importantly, living in a seismic zone does not mean constant danger. Most earthquakes are small. Larger ones are rare. Human adaptation through building codes, early warning systems, and public awareness transforms natural processes into manageable challenges. As you rest, imagine Earth's seismic zones not as scars, but as seams, places where the planet gently adjusts, breathes, and reshapes itself. These zones are signs of a living world, not a hostile one. As your breathing slows and the world around you feels still, let's gently move beneath the surface of the Earth and explore what actually happens during an earthquake. Not with urgency or noise, but with calm curiosity, following the soft journey of seismic waves as they ripple through rock and soil. When an earthquake begins, it starts at a point deep underground called the focus or hypocenter. This is where accumulated stress along a fault finally releases. The energy doesn't stay in one place. Instead, it travels outward in all directions, like slow-moving ripples across a quiet lake. These ripples are known as seismic waves, and they are the reason earthquakes can be felt far from where they begin. Seismology, the science that studies these waves, has helped humanity understand the hidden interior of our planet, much like medical imaging reveals the inner workings of the human body. The first waves to leave the focus are called primary waves, or P waves. They are the fastest seismic waves and arrive first at seismic stations. P waves move by compressing and expanding the material they pass through, similar to sound waves traveling through air. Because of this motion, P waves can move through solids, liquids, and even gases. They pass easily through rock, water, and molten material deep within the earth. Their speed and versatility make them especially useful for scientists studying the planet's internal layers. Following closely behind are secondary waves, or S waves. These waves move more slowly and arrive after P waves. Instead of compressing material, S waves shake it from side to side, or up and down. S waves can only travel through solids. They cannot move through liquids. This simple fact led to one of the most important discoveries in Earth science: the realization that Earth's outer core is liquid. When scientists observed that S waves disappeared at certain depths, they understood that something fluid lay beneath the solid mantle. After the body waves, P waves, and S waves, come surface waves. These waves travel along Earth's surface rather than through its interior. They are slower, but they often cause the strongest shaking felt by people. There are two main types of surface waves. Love waves move the ground side to side, while Rayleigh waves create a rolling motion, similar to ocean waves. This rolling movement is what many people describe as the Earth gently rising and falling beneath their feet. Despite their power, surface waves follow clear physical laws. Engineers study them carefully to design buildings that can move safely with the ground, rather than resisting it. Modern architecture, especially in earthquake-prone regions, uses flexible materials and shock-absorbing technology inspired by these wave patterns. Seismic waves don't only tell us about earthquakes, they are also tools for exploration. By analyzing how waves travel through Earth, scientists map underground structures, locate natural resources, and study the planet's composition. This technology supports industries like energy, construction, and environmental science, linking geology with global economies and technological innovation. Even luxury architecture and tourism developments in seismic regions rely on seismic data to ensure safety and long-term sustainability. Seismographs are the instruments that record seismic waves. They sit quietly in laboratories and remote stations around the world, continuously listening to Earth's movements. Most of the time, they record tiny vibrations that humans never notice. These small signals are called microseisms. They can be caused by ocean waves crashing against coastlines, strong winds, or even traffic in large cities. Earth is never truly still. It is always humming softly beneath our feet. When a larger earthquake occurs, seismographs capture detailed wave patterns. Scientists can determine the earthquake's location, depth, and magnitude by comparing arrival times of different waves at multiple stations. This global network allows earthquakes to be studied almost instantly, fostering international cooperation and shared knowledge. Data flows across borders, supporting education, disaster preparedness, and scientific research. It's important to remember that seismic waves lose energy as they travel. The farther they go, the gentler they become. This natural fading helps protect distant regions from stronger shaking and reminds us that Earth balances its own forces. As you rest, imagine these waves not as disruptions, but as messages, gentle signals carrying information through stone and time. They connect the deep earth to the surface, the past to the present, and science to daily life. As your thoughts settle and your breathing grows softer, we can continue our gentle journey by exploring how scientists measure earthquakes. Not with alarming headlines or sharp numbers, but with calm clarity. Understanding how these measurements help people around the world live more safely and confidently on a moving planet. When an earthquake happens, one of the first questions people ask is, how big was it? The answer depends on what we mean by big. In earthquake science, there are two main ways to describe size: magnitude and intensity. Though they sound similar, they describe very different things. Magnitude measures the energy released at the source of the earthquake. It is a single number that represents how much energy was unleashed when the fault slipped. No matter where you are in the world, an earthquake has only one magnitude value. The most well-known magnitude scale, developed in the 1930s, while still commonly mentioned in popular culture, scientists today mostly use the moment magnitude scale, which is more accurate for large earthquakes and better reflects the physics of fault movement. The moment magnitude scale is based on three factors: the area of the fault that slipped, the amount of slip, and the rigidity of the rocks involved. Together, these elements describe how much energy was released into the earth as seismic waves. Because the scale is logarithmic, each whole number increase represents about 32 times more energy release. This means a magnitude 6 earthquake releases far more energy, 5, even though the numbers appear close. Despite this, magnitude alone does not tell us how an earthquake feels in a specific place. That is where intensity comes in. Intensity describes the effects of an earthquake at a particular location. It considers how strongly the ground shakes, how people perceive the motion, and what kind of damage occurs. Intensity can vary widely from place to place during the same earthquake. The most commonly used intensity scale is the modified Mercalli intensity scale. Instead of numbers, it uses Roman numerals from I to 12. A low intensity might mean the shaking was barely felt, while higher intensities describe stronger motion and visible effects. For example, an earthquake might have a high magnitude but low intensity in a distant city. Or it might have moderate magnitude but high intensity near the epicenter, especially if the ground conditions amplify shaking. Soil type plays a major role in intensity. Soft soils, such as river sediments or reclaimed land, tend to amplify seismic waves. This is why cities built near rivers or coastlines sometimes experience stronger shaking than nearby areas built on solid rock. Understanding this has shaped modern urban planning and real estate development. Engineers now carefully consider ground conditions when designing buildings, especially in major economic centers and tourist destinations where safety is essential. High-rise hotels, cultural landmarks, and transportation hubs are often built with advanced seismic design techniques. These include flexible foundations, base isolation systems, and energy-dissipating structures that gently absorb motion rather than resisting it. Earthquake measurement also helps emergency responders prioritize aid. Intensity maps show where shaking was strongest, guiding rescue efforts and infrastructure inspections. This rapid information flow saves lives and supports recovery. Technology plays a quiet but powerful role here. Automated systems analyze seismic data in seconds, sending alerts to emergency services, utilities, and transportation networks. In some regions, early warning systems can even slow trains or shut down sensitive equipment before shaking arrives. These systems rely on the fact that P waves travel faster than the more damaging S waves and surface waves. By detecting P waves first, alerts can be issued moments before stronger shaking reaches populated areas. Though the warning time may be brief, even a few seconds can make a difference. Elevators can stop, surgeons can pause, and people can move to safer positions. This is a beautiful example of science serving daily life in calm, practical ways. It's also important to remember that numbers alone do not define an earthquake's impact. Social factors, building quality, preparedness, and education all shape outcomes. Countries that invest in earthquake awareness and resilient infrastructure often experience less damage, even from powerful events. Education plays a central role here. When people understand how earthquakes work and what measurements mean, fear is replaced with knowledge. Calm replaces panic. Preparation replaces surprise. As you rest, imagine these measurements not as cold data, but as gentle tools, ways humans listen to Earth. Learn from it and live alongside it more wisely. As the rhythm of the Earth continues beneath us, we now drift into a gentle explanation of why earthquakes seem to visit some regions again and again, while other places remain quiet for centuries. This pattern is not random. It is shaped by the slow, graceful movement of tectonic plates, moving across the planet like vast floating continents on a deep, unseen sea. The Earth's outer shell, called the lithosphere, is divided into several large tectonic plates and many smaller ones. These plates move slowly, typically just a few centimeters each year, about the speed at which fingernails grow. Though the motion is gentle, the forces involved are immense. Earthquakes tend to cluster along the boundaries where these plates meet. These boundaries form long, winding zones of geological activity that shape mountains, ocean basins, volcanoes, and earthquakes alike. There are three main types of plate boundaries, and each one produces earthquakes in its own quiet way. The first type is the convergent boundary, where plates move toward each other. When an oceanic plate meets a continental plate, the denser oceanic plate often slides beneath the other in a process called subduction. This movement builds deep ocean trenches and powerful earthquakes. Some of the world's most well-known earthquake zones are located along these subduction boundaries. The Pacific Ring of Fire, which arcs around the Pacific Ocean, is a prime example. This region includes parts of Japan, Indonesia, Chile, Alaska, and New Zealand. Despite its dramatic name, life along the Ring of Fire continues calmly, day to day. Cities thrive, cultures flourish, and economies grow. Supported by careful planning and resilient infrastructure, informed by generations of geological knowledge. The second type of boundary is the divergent boundary, where plates move away from each other. As they separate, magma rises from below to fill the gap, creating new crust. These boundaries are often found along mid-ocean ridges, hidden beneath thousands of meters of water. Earthquakes at divergent boundaries are usually smaller and gentler. They occur as the crust stretches and cracks, releasing tension in soft, rolling motions rather than sudden jolts. In some places, divergent boundaries appear on land. Iceland is a peaceful example, where volcanic landscapes, geothermal energy, and tourism coexist atop a slowly spreading plate boundary. The third type is the transform boundary, where plates slide past each other horizontally. Instead of colliding or pulling apart, they move side by side. Stress builds as the plates lock, then releases suddenly as they slip. The San Andreas Fault in California is a well-known transform boundary. Along it, the Pacific Plate and the North American Plate move slowly past each other, shaping the region's geology, landscapes, and long-term planning. Living near such boundaries has influenced architecture, education, and technology. Earthquake-resistant design has become a cornerstone of modern urban development, especially in global cities where tourism, finance, and culture converge. Not all earthquakes occur directly at plate boundaries. Some happen within plates, far from the edges. These intraplate earthquakes are less common, but still significant. They occur when ancient faults deep within plates reactivate under stress. The New Madrid seismic zone in the central United States is one example. Though far from plate boundaries, it experienced strong earthquakes in the early 1800s. These events remind us that Earth's interior remembers its ancient fractures, even when the surface appears calm. The frequency of earthquakes in a region also depends on how fast plates are moving and how locked faults are. Fast-moving plates that remain locked for long periods tend to produce larger earthquakes when they finally slip. In contrast, faults that slip more frequently may release energy in smaller, more manageable events. This gradual release can sometimes reduce the buildup of extreme stress. Scientists monitor these patterns using GPS stations that measure plate motion with astonishing precision. These tools allow researchers to track movement millimeter by millimeter, helping forecast long-term seismic behavior. This data supports disaster preparedness, insurance planning, and infrastructure investment. It influences where bridges are built, how pipelines are designed, and how cities grow sustainably over time. Tourism, too, adapts quietly to seismic geography. Hotels, resorts, and cultural landmarks in earthquake-prone areas are often built with advanced safety features, ensuring travelers can explore the world with confidence and peace of mind. As you rest, imagine the Earth's plates drifting slowly beneath you, not with urgency or danger, but with steady patience. Their movement is part of a grand cycle that has shaped continents, oceans, and human history itself. As we continue drifting through the calm science of earthquakes, we now turn our attention to something almost poetic in its motion: the way earthquake energy travels through the earth as waves. These waves are not chaotic or random, carrying information about the planet's deep interior and quietly shaping how we experience earthquakes at the surface. When an earthquake occurs, energy is released from the focus, the point deep underground where rocks finally give way. From this point, seismic waves spread outward in all directions, much like gentle ripples expanding across the surface of a still lake. There are two main categories of seismic waves which travel through the interior of the Earth, and surface waves which move along the Earth's outer layers. Each type has its own character, speed, and effect. The first body wave is called a primary wave, or P wave. These are the fastest seismic waves and are always the first to arrive at seismic stations. P waves move by compressing and expanding the material they travel through, similar to how sound waves move through air. Because of this motion, P waves can pass through solids, liquids, and gases. They travel easily through rock, magma, and even Earth's liquid outer core. Their speed allows scientists to use them as early warning signals, sometimes giving people a few seconds to prepare before stronger shaking arrives. Following the P waves come secondary waves, or S waves. These move more slowly and create a side-to-side motion, shaking the ground perpendicular to the direction of travel. Unlike P waves, S waves can only move through solid material. This limitation has helped scientists discover one of the most important facts about Earth's interior. The outer core is liquid. When S waves disappear as they travel through the planet, it reveals where solid rock gives way to molten metal. Although S waves arrive after P waves, they often cause more noticeable shaking. Buildings sway, trees rustle, and objects gently shift as the wave energy passes. Then there are surface waves, which move along Earth's crust and upper layers. These waves travel more slowly than body waves, but they tend to produce the strongest ground motion at the surface. Two main types of surface waves are love waves and Rayleigh waves. Love waves move the ground side to side, while Rayleigh waves roll the ground in a motion similar to ocean waves. This rolling movement can feel like the Earth is breathing slowly beneath your feet. It is this motion that often causes the most visible effects during an earthquake, even when the event itself is moderate in size. The speed and behavior of seismic waves depend on the materials they pass through. Dense, solid rock allows waves to move faster, while softer sediments slow them down and amplify their motion. This is why some cities experience stronger shaking than others during the same earthquake. Urban areas built on soft soils or ancient riverbeds may feel waves more intensely than regions built on bedrock. Understanding wave behavior helps engineers design safer buildings. Skyscrapers, bridges, and transportation systems are carefully engineered to absorb and dissipate wave energy, protecting lives and investments. Modern architecture in earthquake-prone regions blends safety with aesthetics, allowing cities to remain beautiful, functional, and resilient. This thoughtful design supports tourism, business travel, and long-term economic stability. They detect even the smallest vibrations, translating ground motion into precise data. Each earthquake leaves behind a unique wave pattern, like a fingerprint. By studying these patterns, scientists can estimate an earthquake's location, depth, and magnitude. They can also learn about the structure of the Earth itself, using waves to map layers thousands of kilometers below the surface. This research has advanced education, technology, and international cooperation. Seismic data is shared globally, fostering collaboration across borders and supporting disaster preparedness worldwide. Even when no earthquakes are happening, Earth hums quietly with microseisms caused by ocean waves, wind, and human activity. These constant vibrations remind us that the planet is always in motion, even during peaceful moments. As you rest, imagine seismic waves moving gently through the Earth, not as threats, but as messengers carrying stories from deep below. They rise, pass, and fade, leaving calm behind them. As we continue our calm exploration of earthquake science, we now arrive at a topic that often sounds technical, yet becomes surprisingly gentle when understood clearly. This is the quiet art of measuring earthquakes, not just how strong they are, but how they are felt, recorded, and interpreted. When people hear that an earthquake was a certain magnitude, it can sound like a single, simple number. But behind that number is a careful system designed to describe how much energy the Earth released without drama or exaggeration. Earthquake magnitude measures the total energy released at the source of the earthquake. It does not change from place to place. Whether recorded in a quiet desert or a busy coastal city, the magnitude remains the same. For many years, the most famous scale was the Richter scale. Developed in the 1930s, it was designed to measure earthquakes in Southern California. While groundbreaking at the time, it had limitations, especially for very large earthquakes. Today, scientists use the moment magnitude scale, often abbreviated as MW. This scale is more accurate across the full range of earthquake sizes and better reflects the physical properties of fault movement. The moment magnitude scale considers three main factors: the area of the fault that slipped, the amount of movement along the fault, and the rigidity of the rocks involved. Together, these create a precise picture of the earthquake's true energy. Each whole number increase on the magnitude scale represents about 32 times more energy release. This means a magnitude 7 earthquake releases far more energy than a magnitude 6, even though the numbers appear close. Despite this exponential increase, magnitude alone does not tell the full story of how an earthquake feels to people on the surface. That experience is described by intensity. Earthquake intensity measures the effects of shaking at specific locations. It describes how people felt the shaking, how buildings responded, and what changes occurred in the landscape. The most widely used intensity scale is the modified Mercalli intensity scale. It uses Roman numerals from I to 12, with I being not felt and 12 representing total destruction. Lower intensity levels might include subtle vibrations, gently swinging lamps, or faint sounds. Higher levels may involve cracked walls, fallen chimneys, or ground movement. Unlike magnitude, intensity varies from place to place. A single earthquake can produce many different intensity levels, depending on distance from the epicenter. Local geology and building design. Soft soils can amplify shaking, increasing intensity even when magnitude remains moderate. Bedrock, by contrast, tends to reduce motion, allowing energy to pass through more smoothly. This understanding has influenced urban planning and luxury real estate development in seismic regions. Cities now consider ground composition carefully, balancing safety with long-term economic growth. Seismic intensity maps are created after earthquakes to show how shaking varied across regions. These maps help governments, educators, and emergency planners understand risk patterns and improve preparedness. Modern technology allows intensity data to be collected not only from instruments but also from people. Smartphone apps and online reports contribute valuable information, blending human experience with scientific measurement. This combination of data strengthens public education and supports global disaster response systems. It also empowers individuals to participate in science simply by sharing what they felt. Early warning systems rely heavily on magnitude estimation. By detecting P waves quickly, computers can estimate an earthquake's size before stronger waves arrive, offering seconds of warning. Those few seconds can slow trains, pause surgeries, and allow people to take protective actions. This quiet advance in technology saves lives without demanding attention. Understanding magnitude and intensity also helps travelers and tourists make informed decisions. Earthquake-prone regions often remain safe, vibrant destinations thanks to thoughtful engineering and preparedness. From Japan's resilient cities to California's flexible architecture, modern design blends culture, innovation, and safety. These regions continue to thrive economically while respecting Earth's dynamic nature. Even historical earthquakes are reanalyzed using modern techniques. Scientists study old records, damage reports, and geological clues to estimate magnitudes and intensities from centuries ago. This work enriches history and deepens our understanding of how civilizations have adapted to seismic environments over time. It reminds us that humanity has always lived alongside Earth's movements. As you relax, imagine these measurements not as warnings, but as quiet translations, numbers and scales gently turning Earth's motions into understanding. As we move forward in our calm journey through earthquake science, we now turn our attention to geography. Not maps filled with sharp lines or alarming colors, but a slow, thoughtful understanding of where earthquakes tend to occur and why certain regions of our planet quietly experience more seismic activity than others. Earthquakes are not evenly distributed across the globe. Instead, they follow patterns shaped by the slow movement of tectonic plates, drifting at speeds similar to the growth of fingernails. These movements create zones where Earth regularly releases stored energy. One of the most well-known of these regions is the Pacific Ring of Fire. This vast horseshoe-shaped zone surrounds the Pacific Ocean and accounts for about 75% of the world's active volcanoes and roughly 90% of recorded earthquakes. Despite its dramatic name, the Ring of Fire is not a single line of danger. It is a complex network of subduction zones transforms faults and spreading centers that stretch across continents and oceans alike. Countries such as Japan, Indonesia, Chile, New Zealand, and parts of the western United States lie along this region. Over time, these areas have developed advanced engineering, disaster, education, and resilient infrastructure. Japan, for example, blends cutting-edge technology with cultural tradition to create cities designed to sway gently rather than resist violently. Skyscrapers there move almost like trees in the wind, absorbing seismic energy gracefully. Along the western edge of the Americas, subduction zones occur where oceanic plates sink beneath continental plates. These interactions produce some of the largest earthquakes ever recorded, including events off the coasts of Chile and Alaska. Yet, not all earthquake zones involve subduction. Transform boundaries, where plates slide past one another, also generate frequent seismic activity. The San Andreas Fault in California is a well-known example. Along this fault, the Pacific Plate and North American Plate move horizontally, building tension that is released in regular earthquakes. While often moderate in magnitude, these events are closely monitored due to population density. In contrast, divergent boundaries, where plates move apart, produce earthquakes that are usually smaller and gentler. These occur along mid-ocean ridges, such as the Mid-Atlantic Ridge, hidden beneath deep waters. Though mostly unnoticed by humans, these underwater earthquakes play a crucial role in shaping Earth's crust. They create new ocean floor and support marine ecosystems around hydrothermal vents. Beyond plate boundaries, there are also intraplate earthquakes. These occur far from plate edges and can seem surprising. Examples include earthquakes in Central Asia, Eastern North America, and parts of Australia. Intraplate earthquakes often result from ancient faults reactivating under modern stress conditions. While less frequent, they remind scientists that Earth's interior remains dynamic everywhere. The New Madrid seismic zone in the central United States is a classic example. In the early 1800s, this region experienced powerful earthquakes felt across much of the continent, despite being far from any plate boundary. Understanding these zones helps governments plan infrastructure investments wisely. Transportation networks, energy systems, and urban development all benefit from seismic awareness. Luxury resorts, tourism hubs, and cultural heritage sites are increasingly designed with earthquake resilience in mind. This allows travelers to explore earthquake-prone regions safely while supporting local economies. Mediterranean regions also experience frequent seismic activity due to complex plate interactions involving Africa, Eurasia, and smaller microplates. Italy, Greece, and Turkey sit atop zones shaped by millions of years of geological motion. These areas combine ancient history with modern engineering, showing how long-term adaptation can turn seismic risk into cultural strength. In Asia, the Himalayan region marks a powerful collision between the Indian and Eurasian plates. This ongoing convergence uplifts mountains and produces earthquakes across Nepal, northern India, and surrounding areas. Here, seismic activity is tied directly to the creation of Earth's highest peaks. The same forces that raise mountains also generate deep and shallow earthquakes over time. Africa's Great Rift Valley offers another perspective. This is a region where the continent is slowly splitting apart, forming new plate boundaries. Earthquakes here are often shallow and associated with volcanic activity. These rift zones provide scientists with a living laboratory to study how continents break apart, a process that takes tens of millions of years. Oceans hide many earthquake zones that rarely make headlines. Submarine earthquakes occur daily, reshaping seafloor landscapes and influencing ocean circulation. Some underwater earthquakes generate tsunamis, but many pass quietly, recorded only by instruments. These subtle events remind us that Earth is constantly adjusting, even when we do not feel it. Modern seismic networks monitor these zones continuously. Thousands of seismometers around the world feed data into global systems, supporting education, research, and early warning technology. This data also informs insurance markets, urban planning, and international aid strategies. Accurate risk assessment supports economic stability and long-term development. For individuals, a sense of calm can come from understanding earthquake zones. Knowledge replaces uncertainty, allowing people to live confidently even in active regions. Children in earthquake-prone areas often grow up learning safety drills calmly, integrating preparedness into everyday life without anxiety. As you rest, imagine the planet breathing slowly, tension building, releasing, and restoring balance over time. Earthquake zones are not signs of chaos, but expressions of natural rhythm. As our gentle exploration continues, we now turn to the quiet conversation between earthquakes and human creativity. This is the story of how people across cultures and centuries have learned not to fight the shaking ground, but to adapt to it. It is a calming reminder that knowledge, patience, and thoughtful design can transform natural risk into everyday resilience. For most of human history, earthquakes were mysterious events. Ancient builders observed patterns through experience rather than instruments. Over time, those observations shaped architecture in subtle and effective ways. In traditional Japanese homes, flexible wooden frames and lightweight materials allowed buildings to sway rather than collapse. This approach was not based on modern equations, but on generations of lived wisdom passed down quietly. Similarly, ancient Andean civilizations used precisely cut stone blocks without mortar. These stones could move slightly during earthquakes, settling back into place afterward. Many of these structures still stand today, centuries later. Modern earthquake engineering builds upon this intuitive understanding. Today's goal is not to create buildings that never move, but buildings that move safely. Seismic design begins with understanding how seismic waves travel through different materials. Soft soils amplify shaking, while solid bedrock tends to reduce it. This knowledge guides where and how cities expand. Urban planners now consider geology alongside economy, tourism, and cultural heritage. Major global cities integrate seismic data into zoning laws, protecting both residents and long-term investments. One of the most important innovations in earthquake engineering is base isolation. This technique places flexible bearings or sliders between a building and its foundation. During an earthquake, these systems absorb and redirect energy, allowing the ground to move beneath the structure, while the building itself remains relatively calm. Hospitals, museums, luxury hotels, and data centers often use base isolation to protect both people and valuable assets. This technology supports continuity in healthcare, tourism, and global business. Another approach is energy dissipation, using dampers similar to shock absorbers. These devices convert kinetic energy into heat, reducing the force transmitted through a structure. Skyscrapers in earthquake-prone cities often combine dampers with tuned mass systems. These large weights, hidden within a building, counteract motion by moving in the opposite direction of the shaking. The result is a slow, controlled sway that occupants may barely notice. From inside, the experience can feel surprisingly peaceful, even during significant seismic events. Building codes play a central role in this process. They are living documents, updated regularly as new research emerges. Each earthquake teaches engineers something new. After major earthquakes, teams analyze how buildings performed. What failed, what succeeded, and why. These lessons ripple outward, improving construction practices worldwide. In many regions, retrofitting older buildings is just as important as designing new ones. Schools, bridges, and historic landmarks are strengthened using modern techniques that respect original aesthetics. This balance between preservation and safety is especially important for cultural heritage sites. Ancient temples, cathedrals, and monuments represent shared human history. Engineers use non-invasive methods such as fiber reinforcement, internal bracing, and discrete base isolation to protect these treasures without altering their appearance. Bridges are another critical focus. They connect economies, enable travel, and support emergency response. Modern seismic bridge design allows sections to move independently without collapsing. Expansion joints, flexible supports, and sacrificial components help bridges absorb seismic forces, and remain usable after earthquakes. Even household design reflects seismic awareness. Securing furniture, using flexible gas lines, and choosing resilient materials all contribute to safer living environments. Education plays a quiet but powerful role. Communities that understand how buildings behave during earthquakes tend to respond with calm and confidence. Simple knowledge, such as standing in doorways, being outdated advice, or knowing safe spots within rooms, reduces panic and supports better outcomes. In earthquake-prone regions, preparedness is woven into daily life. Drills are practiced gently, without fear, reinforcing routine rather than alarm. Technology now supports this preparedness through early warning systems. These systems detect seismic waves near their source and send alerts before strong shaking arrives. Even a few seconds of warning can allow trains to slow, surgeries to pause, and people to take protective action. This blend of science and technology saves lives quietly. Mobile apps and public alert systems extend these benefits to millions, integrating safety into modern digital lifestyles. From an economic perspective, resilient design reduces long-term costs. Buildings that survive earthquakes minimize reconstruction expenses and business interruption. Insurance industries rely on seismic models to assess risk accurately. This supports fair pricing and encourages safer construction practices. Tourism also benefits from earthquake resilience. Travelers are more confident visiting regions where infrastructure is designed thoughtfully. Luxury resorts in seismic zones often showcase their engineering as part of their appeal, blending comfort with cutting-edge safety. Sustainable design aligns naturally with seismic resilience. Flexible materials, modular construction, and adaptive reuse support both environmental and structural goals. In this way, earthquake engineering connects to broader themes of sustainability, education, and global development. Perhaps most comforting is the philosophy underlying modern seismic design. It accepts that earthquakes will happen and focuses instead on minimizing harm. This approach mirrors a gentle mindset, acknowledging natural forces without fear, responding with preparation rather than resistance. As you relax, imagine buildings breathing with the earth, swaying softly, absorbing motion, and returning to stillness. As we continue drifting gently through the science of earthquakes, we now arrive at a quieter, almost meditative topic: measurement. This is the story of how scientists listen to the earth, translating tiny movements into knowledge that protects lives, cities, economies, and cultures across the globe. Earthquakes begin deep below our feet, often far beyond human senses. Long before we feel shaken, the planet is already whispering through vibrations, traveling silently through rock. To hear these whispers, scientists use instruments called seismometers. These devices are designed with remarkable sensitivity, capable of detecting motion smaller than the width of a human hair. A basic seismometer consists of a suspended mass and a fixed frame. When the ground moves, the frame shifts while the mass remains relatively still due to inertia. This difference in motion is recorded as a signal. Modern seismometers are far more advanced, using electronic sensors, lasers, and digital processing to capture precise ground motion in 3 dimensions. These instruments are placed all over the world, from busy cities to remote deserts, polar regions, and deep ocean floors. Together, they form global seismic networks. Some seismometers sit quietly beneath luxury hotels, universities, and research centers, integrating science into everyday environments without disruption. Others are buried deep underground to reduce interference from traffic, wind, or human activity. Silence improves accuracy. When an earthquake occurs, seismic waves spread outward in all directions. Different waves arrive at different times, each carrying unique information. Primary waves, or P waves, arrive first. They move quickly, compressing and expanding rock-like sound waves. Secondary waves, or S waves, follow more slowly, shaking the ground side to side. Surface waves arrive last, but often cause the most damage, rolling along Earth's surface in complex patterns. By comparing the arrival times of these waves at multiple stations, scientists can pinpoint an earthquake's location with remarkable precision. The depth of an earthquake is just as important as its location. Shallow earthquakes tend to cause more surface damage, while deeper ones may be felt over wider areas, but with less intensity. Magnitude is another key measurement. It describes the total energy released by an earthquake. The moment magnitude scale, now widely used, provides a consistent way to compare earthquakes of all sizes. Each whole number increase represents about 32 times more energy release. This exponential scale helps explain why even small increases in magnitude can dramatically change an earthquake's impact. Intensity, by contrast, describes how an earthquake feels at specific locations. This depends on distance, soil type, building design, and local geography. Intensity scales, such as the modified Mercalli scale, are based on observations: what people felt, what objects moved, and how structures responded. In modern times, intensity data is often collected through online reports. People around the world contribute observations, blending citizen science with professional research. These reports help scientists understand how earthquakes interact with real-world environments, including cities, infrastructure, and cultural landmarks. This information shapes building codes, guides urban planning, and informs investment decisions in travel, tourism, and global development. In regions with frequent seismic activity, real-time monitoring supports early warning systems. These systems detect the first arriving P waves and issue alerts before stronger shaking begins. Even a brief warning can make a meaningful difference. Elevators can stop, trains can slow, industrial systems can shut down safely, and people can take protective action. Behind these alerts is a calm, automated process running quietly in the background, designed to reduce chaos rather than amplify fear. Ocean-based monitoring adds another layer of understanding. Seafloor sensors detect earthquakes beneath the oceans, where many major fault zones lie. These sensors are critical for tsunami warning systems, helping coastal communities prepare calmly and efficiently. Satellite technology also plays a role. Using a technique called interferometric synthetic aperture radar, or INSAR, scientists can measure ground deformation from space by comparing satellite images taken before and after an earthquake. Researchers can see how the Earth's surface shifted, sometimes by just a few centimeters. These maps reveal fault movement patterns and help refine models of tectonic behavior. Technology continues to evolve. Smartphone sensors, for example, are increasingly used to supplement traditional seismic networks. Millions of phones, when combined, can act as a distributed sensor system, detecting, shaking, and sharing data almost instantly. This democratization of science integrates earthquake monitoring into everyday life, blending technology, education, and safety seamlessly. Artificial intelligence and machine learning now help analyze massive datasets, identifying subtle patterns that humans might miss. These tools improve earthquake forecasting research, though precise prediction remains beyond current scientific capability. Scientists emphasize an important distinction. Earthquakes cannot yet be predicted with exact timing, but they can be anticipated probabilistically. Hazard maps show where earthquakes are more likely over long periods, guiding safer development and informed decision-making. These maps influence everything from insurance pricing to infrastructure investment and tourism planning. In this way, earthquake science quietly supports global economies, ensuring resilience rather than reaction. Public communication is another essential element. Scientists strive to present information clearly and calmly, avoiding alarmist language. Educational outreach helps communities understand what measurements mean and how to respond appropriately. This trust between scientists and the public supports smoother responses when earthquakes occur. Museums, science centers, and educational programs often include seismic exhibits, inviting curiosity rather than fear. Visitors can watch simulated seismic waves, feel gentle shaking platforms, and learn how the earth moves beneath them. These experiences transform abstract data into tangible understanding, fostering respect for natural forces. For many, earthquake monitoring becomes a symbol of humanity's relationship with the planet, attentive, adaptive, and thoughtful. As you relax, imagine the earth sending quiet signals through stone, and scientists listening patiently, translating motion into insight. This ongoing dialogue between planet and people continues day and night, regardless of whether we are awake or asleep. As we arrive at the final part of our journey, everything gently comes together. The science, the history, the quiet measurements, and the human stories all merge into a single, calming realization. Earthquakes are not interruptions to Earth's story. They are part of it. Our planet is alive in a slow, patient way. Continents drift at the pace of growing fingernails. Mountains rise grain by grain. Oceans open and close over millions of years. Earthquakes are simply brief moments when that deep, steady motion becomes visible. From space, Earth appears serene. Swirls of clouds drift over blue oceans and green land. There is no hint of the immense forces at work beneath the surface. Yet, those forces are what shaped every coastline, valley, and the plateau we know today. Without tectonic movement, there would be no towering mountain ranges to inspire travelers, no fertile volcanic soils that support agriculture and global economies, and no dynamic landscapes that draw tourism and cultural imagination. Earthquakes remind us that the ground beneath our feet is not static. It is part of a living system, constantly adjusting, balancing, and renewing itself. Human history has always unfolded alongside this movement. Ancient civilizations learned to read the land, choosing where to build, farm, and trade based on natural patterns. Modern cities continue this tradition, now supported by science, technology, and education. Skyscrapers sway gently by design. Bridges flex. Infrastructure adapts. Rather than resisting Earth's motion, engineers and planners increasingly work with it. This philosophy of resilience reflects a mature relationship with nature. In many cultures, earthquakes have inspired stories, myths, and art. They appear in poetry, religious texts, and oral traditions, often symbolizing transformation or renewal. Today, science offers a different lens, one grounded in observation rather than myth, yet still filled with wonder. Understanding earthquakes does not remove their power, but it replaces fear with context. Knowledge allows us to prepare calmly, respond thoughtfully, and recover with intention. This approach benefits not only safety, but also emotional well-being. Calm understanding reduces anxiety, especially when learning occurs in gentle, reassuring ways. That is why calm, educational storytelling plays such an important role in science communication. By presenting complex topics slowly and softly, we create space for curiosity instead of tension. This is especially meaningful when learning happens at night, when the mind is open and relaxed. As you listen, your body remains at rest, while your imagination travels through fault lines, continents, and deep time. You may picture the San Andreas Fault stretching quietly across California, or the Mid-Atlantic Ridge rising invisibly beneath the ocean. You may imagine ancient earthquakes shaping landscapes that are now home to bustling cities, luxury resorts, and cultural landmarks. Each place carries layers of history beneath its streets, shaped by movement long before humans arrived. This awareness fosters humility. It reminds us that our cities, economies, and technologies exist within a much larger system. At the same time, it highlights human ingenuity. Despite living on a moving planet, we build, travel, learn, and dream. Education plays a central role in this balance. By teaching geology alongside history, culture, and technology, we create a more complete understanding of our world. Students learn that science is not separate from daily life. It influences architecture, insurance, urban design, and even tourism. Travelers visiting earthquake-prone regions often encounter museums and information centers that explain local geology with pride. These places celebrate resilience rather than danger, inviting visitors to appreciate the dynamic earth beneath their journey. Luxury hotels in seismic zones quietly incorporate advanced engineering, offering comfort without drawing attention to complexity. This seamless integration of science into daily experience reflects progress. It shows that understanding natural forces does not diminish beauty or peace. It enhances them. As climate awareness grows, earthquake science also contributes to broader conversations about Earth systems. Plate tectonics influences volcanic activity, ocean circulation, and long-term climate patterns. Nothing exists in isolation. Every system is connected. Recognizing these connections helps us think globally while acting locally. It encourages cooperation across borders, cultures, and disciplines. International seismic networks share data freely, transcending politics in service of shared knowledge. This global collaboration mirrors the interconnected nature of the planet itself. As you rest, consider how quiet this cooperation is. There is no fanfare, only steady listening and patient analysis. Day and night, sensors record motion. Scientists interpret signals. Engineers refine designs. Life continues. Earth continues. And in this continuity, there is comfort. Earthquakes, when understood, become reminders of stability within change. They show that movement does not mean chaos. It means adjustment. Just as the planet releases stress gradually, so can we. By slowing our breathing, easing our thoughts, and trusting in preparation and knowledge, we align ourselves with the planet's rhythm. There is no need to stay alert. The systems are in place. The science is ongoing. You are safe to rest. As this journey concludes, allow your thoughts to drift like tectonic plates beneath an ocean, slow and effortless. Let curiosity soften into calm. Let knowledge become reassurance. Thank you for spending this quiet time exploring Earth's hidden motions. If you've enjoyed this gentle exploration of earthquake facts and tectonic science, feel free to revisit any part whenever you need calm understanding. Now, rest comfortably, knowing that the planet continues its ancient dance, steady and patient beneath a sleeping world.